Hello everybody. So we're starting a new topic today. I think you'll find it fairly simple and straightforward, short, easy to learn. We're essentially learning how to use two formulas. They are in the topics arc length and sector area. In the notes here, what you see, the arc is highlighted in yellow. So that is a section of a circle. You'll recall from basic geometry that the outside of the circle, the distance around the circle, is called the circumference. An arc is just a piece of the circumference. You could even say the circumference itself is an arc. It's an arc of 360 degrees. But when we talk about arc length, we're not talking about the degrees of the angle. We're talking about the distance or the length from one point to another point on the circle. If you could see me trace that, hopefully that made sense. Now the angle at the center of that arc is important. And then of course the radius is going to be important. So that's one thing we're going to be figuring out. The next, which is in green, is sector area. So the sector is like the slice of pie, the slice of pizza, the area of that. Of course, a whole circle has an area, a equals pi r squared, if you remember that. But for a section of a circle, called a sector, not a section, that area has its own formula as well. So we need to get familiar with those terms, arc length and sector area. We need to get familiar with the variables we're going to be using. So the central angle is this symbol right here, which I'm going to write again. It's a circle with a horizontal line through it. That is the Greek letter theta, part of the Greek alphabet. Now, theta is, again, the central angle. It is in both formulas that we're going to be using, and it's important that the theta must always be in radians for these formulas to work. That's a standard, that's a given, that's an understood in all of mathematics. Theta, the central angle, has to be in radians. But, spoiler alert, every problem is in degrees. So we're going to have to deal with that. That's a thing we have to deal with. The radius r is important in virtually every problem. S stands for arc length. A was not used for arc because A stands for area. I think L could have been used for length. In my opinion, if I were writing all the rules, I probably would have used L or maybe a cursive L so it doesn't look like a 1. But anyway, what's kind of universally used for arc length is S. So take it for what it is, I don't know. So the formula for arc length, S, no, that's not a 5. Please don't confuse my S's with 5s. S equals theta times r. So the central angle, again, has to be in radians times the radius gives you that length. The sector area is A equals 1/2 theta r squared. A equals 1/2 theta r squared. Again, theta, the angle has to be in radians. But that's it. Learn how to apply these formulas, and we are good to go. So what we're going to look at is a few sector area, we're going to start with arc length problems. Find the length of each arc. A couple without the diagram, because it really shouldn't matter. The diagram helps, but you don't need it. A couple of word problems, which I actually wrote. They're not part of my normal handout, the software that I use. And then we get into some sector area problems, again, with diagrams, a couple without. And then a couple more word problems that had got shoved down the page, and I couldn't figure out how to fix them, so they're up at the top of the page. So it looks like this. Again, I wrote these. When you look at the answer key, you'll see some of the answers are handwritten because they are mine. Okay, so let's get started on this. We are going to be applying both of those formulas. Let's do it. I'm doing the evens, of course. I'll be asking you to do the odds. So find the arc length. Now notice, we're not trying to find this arc length. No, the central angle is here, 300 degrees. So the first thing we need to do is convert that 300 degrees to radians. 300 converted to radians, you know, you multiply by pi over 180. And you know what? I got to cheat for just a second. I think these answers are left in terms of pi. I don't think we're going to use 3.14. Yeah, see all the answers have pi in them. So keep that in mind for right now. Okay, so 300 times pi over 180. If you simplify this, hopefully you know the zeros can cancel. 30 and 18 are left over. You can divide those both by 6, right? 6 goes into 30 5 times, 6 goes into 18 3 times. So this is 5 pi over 3. I think possibly when we first did this before Christmas break, I just did this on the calculator. 300 times pi over 180, you do 300 over 180, then hit the fraction button, 5/3. There's your 5/3, and then just stick pi on the top. So if you're using a calculator, if you forgot how, that's how you can do it on the calculator. So anyway, sector length, so this is S, arc length, good grief, I gotta say it right. S for length, that's really confusing, is theta, which is 5 pi over 3, times r, which is 10. 5 pi over 3 times 10, put the 10 over 1, that's 50 pi over 3. And the unit of measure in this problem is kilometers. So 50 pi over 3 km. And why is this taking me so long just to scroll down? Right there, 50 pi over 3 kilometers. Nothing fancy, that's pretty much it. What I probably could have done is I could have done this all on the calculator except for the pi part. So what was it? 300 times, instead of pi over 180, do 1 over 180, and then times 10, and hit the fraction button, you get 50 over 3, and then put pi up there with a 50, because of the whole radian thing, and then we would have gotten the same answer. So this is pretty easy, straightforward math. So if I want to do this the easiest possible way, I'm going to do pi over 180 times 240, not 244, 240 degrees, that's our theta, times 12. And you can either work this out manually or you can use the calculator. Again, let's say I want to use the calculator. Instead of pi over 180, I'm going to go 1 over 180, and then times 240, and then times 12. So this part of the calculation is what gives me radians. Times 12 is part of the formula. It's the times r part of the formula. All you have to do now is take that answer, which is 16. Oops, sorry about that. 16, stick a pi next to it, and then put the label down, miles. And that had better be the answer to number 4. And it is 16 pi miles. Now the next problem is a little different. There is no diagram. Doesn't really matter. They flat out tell us what theta is and what the radius is. Round the answer to the nearest tenth means we actually are not going to use the pi symbol. We're going to use the value of pi. So here, S equals pi over 180 times theta, which is 210, times r, which is 9. Again, the formula, S equals theta times r. This part here is the theta, just to beat that to death. But sorry if I'm getting carried away. So anyway, I want to type this in the calculator. Now I am going to use the pi button. Pi over 180. Oops, let's get this right. Come on. Pi over 180 times 210 times 9. And this works out to be approximately 32.98. If we round to the nearest tenth, that 9 actually has to round up to 33. So 33, and then the unit of measure is centimeters. So the answer number 6 is going to be 33 centimeters. And there it is, 33.0. So that 0.0 they're indicating that it was actually rounded to the appropriate place. So the formula is pretty straightforward. It looks like it. You just multiply two things together, theta times r. But since theta has to be in radians, and in the problem it's always in degrees, you have to do that extra step of multiplying by pi over 180. You can either do it as a separate step like I did in that first problem, or you can just sort of integrate it all into the same formula and work it out. Use a calculator if it helps. Do it by hand if you'd rather. Of course, for the ones with a decimal, you're going to want to use a calculator. Okay, let's look at the word problems. Now, let's see. If I'm doing the evens, I'm going to be doing 6.2. I'm going to ask you to do 6.1. So here, a fly sits on the end of the minute hand of a clock for 20 minutes. The minute hand is 5 inches long. How far did the fly travel in that time? Sketch a diagram if it helps. So I'm going to sketch a diagram. Here's my clock. Here's my minute hand, which is 5 inches, and in 20 minutes it travels a certain distance. I'll tell you what, just to make this a little bit easier on me, I'm going to say the minute hand, just for sake of argument, started right on the 12, and then 5, 10, 15, 20 minutes later, it ends up right here. The radius, of course, 5. The question is if the little fly, okay, I'm not going to draw a fly, I'm just going to put a little random mark there, was sitting on the end of this minute hand, and then he traveled for 20 minutes and ended up here. Well, we got to do a little reasoning and figure out, okay, what's the theta in this problem? Because once we know what theta is, all we have to do is multiply it by 5, and that'll give us the arc length, which is the distance that that little fly traveled. Just taking his old time, relaxing on a minute hand. So, what is that angle? Well, it's not that complicated. So, you know, the full revolution around a clock is 60 minutes, and if he traveled for 20 out of 60 minutes, that's a fraction, 20 out of 60. 20 out of 60 is the same thing as 1/3, right? So he traveled 1/3 of a circle. Well, 1/3 of a circle, a full circle, is 360 degrees. So 1/3 times 360 is what? 120. 1/3 times 360 is 120. So the theta in this problem is 120 degrees. So our sector length, why can't I write a letter S? Right. Our sector, not sector length, I cannot say this right, guys, I am sorry. Our arc length, S for arc length, is theta times radius. Theta is pi over 180 times 120 times 5. 5 is theta, 120 is the theta in degrees. You multiply it by pi over 180 so that it's in radians, and then you multiply it by 5 because that's the radius. And we're also answering this one to the nearest tenth. So we can just use the pi button on the calculator. Pi over 180 times 120 times 5. And it looks like this is approximately, you know that little funny equal sign means approximately, 10.5, what was it, inches? It was a small clock, right? Yep, 5 inches is the radius. So that fly traveled 10.5 inches. Now let's see if I did it right. Nope, that's the wrong one. 10.5 inches right there. I even included all the steps and everything. So good. So those are all of the problems on arc length. I know I've said sector length a bunch of times. It's because those darn mathematicians chose S to represent arc length. And sector begins with an S, and I'm just not that smart. Boy, how confusing is that. Arc starts with A, so A is area. Sector starts with S, but S is length. Ugh. All right, enough frustration. Let's move along. Let me clear everything out of the calculator and get to the bottom section of the work here. Find the sector area. Now this formula, A equals 1/2 theta r squared. That's the formula for calculating this area right here, or this area right here, right? Well, yeah. Okay, so how do we do this? It's like the last problem where we do have to convert the angle from degrees to radians. You can either do that separately, 255 times pi over 180, get an answer, and then plug that into the formula, or you can just plug it into the formula all at once. I honestly prefer plugging it into the formula all at once. So A equals 1/2, that's part of the formula, times theta, so that's going to be pi over 180 times 255 times r squared, so that's times 19 squared. So in the problems where you're leaving pi as the symbol, right, so that's called leaving your answers in terms of pi. It's the same thing I did in the first section of the worksheet. I'm going to type this all into the calculator, but not with the pi button. So I'm going to go 1/2 times, instead of pi over 180, you just go 1 over 180 times 255 times 19 squared. Ooh, that does not look good. Oh, of course, then you hit the fraction button, right? 6,137 24ths pi square meters. Remember, area is measured in square meters. That's how many squares fit inside this circle. But that is an improper fraction. I wonder if I didn't really pay attention before. Oh no, yeah, the answer is improper. 6,137 pi over 24 square meters. Same exact answer. Where am I? Right there. Good. I thought we were going to do, when you get an improper fraction like 5/2, it's the same thing as 2.5, so you make it a mixed number. I thought we were going to have to do that, but nope. Okay, so number 10. How do we do this? A equals 1/2 times pi over 180 times theta, which is 90, times the radius, 7 squared, right? 1/2 theta r squared. My 7 looks funny. I'm going to change it. So on the calculator, 1/2, heck, you can use 0.5, it's easier to type in, times 1 over 180 times 90 times 7 squared. 12.25, hit the fraction button, that's 49/4. Now the pi from that numerator, just stick it in this numerator. Meters becomes square meters. And that's our area for number 10. Right there. Good. Glad to see I'm not messing this up. Boy, I had a rough morning teaching all my Algebra 2 classes and recording them. I mean, I've made some mistakes, but no, we won't dwell on that. Okay, number 12. Same thing, no diagram, but now we have to round the answer to the nearest tenth. So area equals 1/2 times theta, so that's pi over 180 times 225, times r squared, so that's times 9 squared. But now we're not leaving the answer in terms of pi, we want a decimal value. So 1/2, 0.5, whatever you prefer, times, now I'm going to use the pi button, pi over 180 times 225 times 9 squared. So the area in that sector is 159.0 square kilometers. Let's see if we did number 12 right. Please, please. Yep, right there. And now a couple word problems. I will do number 14. You please do number 13. Dog is chained on the inside corner of a fenced yard. The chain is 36 feet long. The angle created by the sides of the fence is 103 degrees. How much space or what area does the dog have available? Not that I recommend chaining dogs up, but it's a thing, so okay. So let me draw, first of all, here's a fence. Here's the inside corner of a fence, and I'm drawing an obtuse angle because it says the angle created is 103 degrees. And then this dog is on a chain, which is 36 feet long. And I'm not going to draw a dog, but, excuse me, if the dog were to run around, it would create an arc like this, right? The trail of the dog, but it technically has all of this area here available as like living space. I mean, I sure hope you wouldn't have a dog live like this, but yeah, I don't need to, whatever. Okay, so anyway, the question is how much space is there? Or excuse me, how much area is there? I am so sorry. Okay, so area equals 1/2 times theta. So we do 180, 1 over 180, sorry, pi over 180 times 103 degrees times r squared, so times 36 squared. And that looks like a decimal. That needs to be a times, right? So it's 1/2 times theta times r squared. That's the formula we're doing. I hope I didn't hurt your eardrums. Again, we want the answer in rounded off to the nearest tenth, so I'm going to use the pi button. 0.5 times pi over 180 times 103 times 36 squared. And this dog has approximately 1,164.9. Let's see, the chain was 36 feet long, so square feet of living space. Again, not that you would want a dog to live that way, but there you go. Number 13 is more humane. It's about a sprinkler running in the same kind of an idea. It's running in an arc like that. So what surface area of the lawn is getting watered? A lot better than chaining a dog up. All right, let's call that good enough. Please do the odd problems just like I did the evens. And if you have any issues or trouble, contact me and I'll help you out any way I can.